guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So what happens if the central atom has lone pairs instead of actual atoms? So as you can see from this table, which is really useful, depending on the number of lone pairs, you're going to get different molecular structures. And so when you have no lone pairs, these are the structures that we just went over: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. But as soon as you start getting different numbers of lone pairs, you're going to create different molecular geometries. And so I'm going to show you some typical examples of when this is the case. So in the case of tetrahedral, we have CH4, being one of the typical tetrahedral structures. And remember that this bond angle was 109.5 degrees. But what if you have one lone pair? An example of this is NH3, where nitrogen has a lone pair, and then you have a hydrogen, another hydrogen, and another hydrogen. So the lone pair is actually considered as another atom because basically it's an area where there's electrons that are dense. And so it's going to be treated like a tetrahedral molecule because you have 1, 2, 3, 4 numbers of electron dense areas, but it's going to have a different structure. The reason for that is because these lone pairs force the bonding electrons closer together. So these lone pairs are pushing these bonds down and thus making this bond angle smaller. So for NH3, the bond angle is approximately 107 degrees, smaller than what it was for a tetrahedral molecule. So another good example is water. So we all know that water is H2O, and it's going to look like this. But remember, the oxygen has 2 lone pairs. And so let's count both of these as atoms. So it has 4 things that the oxygen is attached to. But now these 2 lone pairs are going to push these hydrogens much further away. And now this angle is going to get even smaller, and it's approximately 105 degrees. So as you can see, going from the molecule with no lone pairs, we actually change the molecular geometry when you incorporate lone pairs. So tetrahedral to trigonal pyramidal to bent. And as you can see, you follow the same kind of pattern for trigonal bipyramidal, where you have the actual structure with no lone pairs, but then as soon as you get one lone pair, you're going to get a different structure, a sawhorse. And then when you get another lone pair, you're going to end up with a T shape. And finally, with 3 lone pairs, you'll get a linear molecule. For octahedral, it's very similar. You start out with 6 atoms bonded to the central atom, and you have octahedral. You get 1 lone pair, you get square pyramidal, 2 lone pairs, square planar, 3 T-shaped, and finally, if all 4 in the same plane are the lone pairs, you get a linear molecule, which is exactly like this linear molecule in terms of the geometry, but it has a completely different number of atoms bound to it / lone pairs. So this is a really important table for you guys to look at and familiarize yourself. So at this point, I also wanted to mention notation that is used in the VS-EPR model. And you might encounter this when you're looking in textbooks or you're looking online for different VS-EPR molecular structures. So the central atom is always labeled A. And then the bonded atoms are labeled X. And then lone pairs are labeled as E. So for example, let's take a look at NH3. So the central atom is nitrogen, You have 3 atoms bound to it, and you also have 1 lone pair. So this is going to take on the form AX3E. On the other hand, for H2O, or water, you have the central atom oxygen bound to 2 atoms and 2 lone pairs. So this is going to be AX2E2. So molecules with the same formula have the same general shape, although their bond angles may differ slightly, as you can see here. And so CH4 or methane and CH3Cl are both AX4. So this is AX4 because you have 4 atoms bound to it with no lone pairs. But even if this was CH3 and then a chlorine instead of the hydrogen, it's going to have the same general formula despite it having a slightly different angle between the different atoms.